Dear students, first we are going to a definition, that is Vandermonde determinant. Vandermonde determinant. What is Vandermonde determinant? So a determinant is of the form D equals determinant Ti power j. A determinant is of the form D equals determinant Ti power j is called a Vandermonde determinant, and its value is given by P equals, D equals product I 1 less than or equals I less than or equals j less than or equals n Ti minus Tj. Consider the products. If Ti equals Tj, this should be vanishes. So this is Vandermonde determinant. Means a determinant D equals determinant Ti power j is called a Vandermonde determinant, and its value is given by D equals product Ti minus Tj, where 1 less than or equals I less than or equals j less than or equals n. If Ti equals Tj, it should be 0. So this D is always anti-symmetric, Ti minus Tj. Okay, so the D is always anti-symmetric. So Vandermonde determinant is always anti-symmetric. Now we are going to a result that is depends upon this determinant. So the theorem states that there is a theorem. The theorem states that the discriminant of any basis, for k equals q theta, the discriminant of any basis for k equals q theta is rational. K equals q theta is rational and non-zero if all conjugates of theta are real. Then the discriminant of any basis is positive. So, how to prove this one? Consider here k equals q theta. Our requirement is the discriminant of any basis for this k equals q theta is rational and non-zero. That's our preliminary requirement. So, consider the basis. Proof is consider the basis. Which are the bases? The basis 1, theta, theta square, etc. theta power n minus 1. If the conjugates of this theta are, what are the conjugates? So the conjugates of theta are theta 1, theta 2, etc. theta n. Then what is delta of, means the discriminant of 1, theta, etc. theta power n minus 1. So delta of 1 theta, theta square, etc. theta power n minus 1 is nothing but it is determinant theta I power j whole square. Why? Because of this is our definition. Okay, means the discriminant that the k equals q theta be of degree n, and alpha 1, alpha 2, etc. alpha n are its basis. Then its discriminant, as discriminant delta of alpha 1, alpha 2, etc. alpha n is nothing but determinant of sigma I alpha j whole square. That's our definition. Means for k equals q theta, if alpha 1, etc. alpha n are basis, k equals q theta of degree n, and if alpha 1, etc. alpha n are basis, then discriminant of this alpha 1, etc. alpha n equals, it is determinant sigma I alpha j whole square. What is sigma I of alpha j? So here it is sigma I of alpha j. We know that sigma I alpha equals alpha I. Also, so here k equals q theta is, the basis of this one is rational and non-zero. That's our requirement. So consider the basis 1 theta, theta square, etc. theta power n minus 1. Hence the conjugates of theta are theta 1, theta 2, etc. theta n. That are the conjugates. then discriminant of 1 theta etc. theta power n minus 1 is nothing but determinant of theta I power j whole square. But we know that according to the Vandermonde determinant, d equals the Vandermonde determinant is defined as d equals determinant of ti power j and is given by its value is product ti minus tj, where I and j are ranges from 1 to n. So according to this argument, therefore what is determinant of, therefore according to this definition, determinant of theta I power j whole square is nothing but product I differs from j. If I equals j, this d vanishes here. I differs from j, here theta I minus theta j. Why? Because it's of the form determinant of theta I power j, but there is a whole square. So here product I differs from j, theta I minus theta j whole square. That means this is nothing but. So finally we have this is delta of 1 theta square etc. theta power n minus 1 is nothing but product I differs from j, it is theta I minus theta j whole square. Okay, so clearly this d is anti-symmetric. So what is this d square? Means it is a square, so d square is always symmetric. Since d square is symmetric, we know that delta is symmetric. So delta is symmetric means this delta is rational. Why? Because here the field is k equals q theta. Okay, so delta is rational. And all of this theta I and theta j are distinct. Theta i's are distinct. We know that theta 1, theta 2 etc. are the k conjugates of this. So are the conjugates of this basis. All of these theta i's are distinct. So since they are distinct, we know that theta I minus theta j differs from 0. So clearly delta is strictly differs from 0, means it is non-zero. Okay. So now let beta 1 etc. beta n or any other basis or any basis. So we know that what is the determinant of discriminant of beta 1 etc. beta n? We know that it is determinant of Cik whole square into discriminant alpha 1 etc. alpha n. This is already defined. We know that determinant of Cik. What is determinant of Cik? Determinant of Cik is always differs from 0. This is non-zero. And we know that delta of alpha 1 etc. alpha n delta is also non-zero. Instead of alpha 1 etc. alpha n, here it is theta 1 etc. theta n. Theta 1 etc. theta n. Clearly this delta is non-zero. Therefore, discriminant of theta 1 etc. theta n are non-zero. Means discriminant is capital delta is non-zero. Determinant is Zik is non-zero. So that means discriminant of this beta 1 etc. beta n is non-zero. And also, what is this delta? This delta is rational. So clearly, according to this equation, surely this discriminant of beta 1 etc. beta n is also rational. Means it is rational and positive. Means non-zero. Agree. So this is our theorem, and this is heavily depends upon the definition Vandermonde determinant. It is of the form, a determinant is of the form d equals ti power j, and whose value is product I differs from j, ti minus tj. Okay. Now we are going to another important concept, which is algebraic integers. What is an algebraic number? We know that algebraic number means a number theta is an algebraic. A number theta is algebraic if there exists a non-zero polynomial f of x such that f of theta equals 0. But what is an algebraic integer? So a complex number, suppose theta is a complex number. A complex number theta is said to be an algebraic integer. An algebraic integer if there exists a non-zero polynomial p of t, a non-zero polynomial, this p of t, with an integer coefficients, p of t with a integer coefficient, that is a crucial point, integer coefficients, and p of t is monic, monic such that p of theta equals 0. A complex number theta which is said to be an algebraic integer if there exists a non-zero monic polynomial. What is a monic polynomial? A polynomial whose highest degree coefficient is 1. That type of polynomial is said to be monic polynomial whose highest degree coefficient is 1. So there exists a monic polynomial, non-zero monic polynomial p of t with the integer coefficient, that is the crucial point, with the integer coefficient such that p of theta equals 0. P of theta equals 0 means it is of the form theta power n plus a n minus 1 theta power n minus theta to the power n minus 1 theta to the power n plus a n minus 1 theta to the power n minus 1 plus etc. plus a2 theta square plus a1 theta plus a0 equals 0. For all ai are integers. For all I, this ai are integers. So theta is a monic, theta is an algebraic integer means there exists a monic polynomial theta power n plus the n minus 1, as monic polynomial equation, that is theta power n plus an minus 1 theta power n minus 1 plus etc. plus a2 theta square plus a1 theta plus a0 equals 0 for all ai following sets. ai are integers. So then the complex number theta is said to be an algebraic integer. So we know that consider theta 1. Theta 1 equals root minus 2. Root minus 2 is a complex number. Root minus 2 is an algebraic integer. Why is it an algebraic integer? Root minus 2, is it an algebraic integer? Sure. Why? Because we know that there exists a monic polynomial theta 1 square plus 2 equals 0. What is theta 1 square? Minus 2. Minus 2 plus 2? 0. Which is a monic polynomial? Sure. Why? Because the highest degree coefficient is 1. Agreed? So, means there exists a polynomial t square plus 2 with an integer coefficient. This coefficient of t square is 1. Coefficient of constant time is 2. Means the constant time is 2. Coefficient of t square is 1 with the integer coefficients. So, this is a theta 1 square plus 2 equals theta 1 square plus 2 is a monic polynomial. So theta 1 equals root minus 2 is an algebraic integer. What about half into 1 plus root of 5? Is it an algebraic integer? Sure. Why? Let it be theta 2. Let theta 2 equals this one. So if you square it, what do you get? Theta 2 square equals, or 4 theta 2 square equals, simply, not 4, theta 2 square equals, it is 1 by 4 into 1 plus root of 5 whole square. Okay, if you rearrange it one, so you will have theta 2 square minus theta 2 minus 1 equals 0. Theta 2 square minus theta 2 minus 1 equals 0. There is again a monic polynomial. Why? Because the highest degree coefficient is 1. Okay, so since it satisfies a monic polynomial, so it is theta 2 means half of 1 plus root of 5 is also an algebraic integer. What about 22 by 7? Let it be theta 3. 22 by 7. Is it an algebraic integer? 22 by 7 satisfies a polynomial. Which one? Means it is 7 theta 3 minus 22 equals 0. Okay, so this is nothing but a polynomial, but which is not monic. So this can be again rearranged as theta 3 minus 22 by 7 equals 0. But 22 by 7 is not an integer. So 22 by 7 is not an algebraic integer. So complex number is an algebraic integer only when it satisfies or there exists a monic polynomial which is such that p of theta equals 0 with the integer coefficients. Agree? So this is the definition of algebraic integer. Theta is an algebraic integer. Then there exists an equation theta power n plus an minus 1 theta to the power n minus 1 plus an minus 2 theta to the power n minus 2 plus etc. plus a1 theta plus a0 equals 0. Okay.